This video is about the electric field. The electric field is very similar to the gravitational field. Rather than having two masses, or a mass, you have a charge sending out this attractive or repulsive force. Alright, charges create electric fields around them, and other charged particles interact with this field, and that's how they feel a force. Just kind of like a mass sends out a gravitational field, and then other masses feel it. Okay? Now, when deciphering or interpreting electric fields, the field is stronger when the lines are closer together. So right here, the field is stronger than it is here, because the lines are closer together. Also, the direction of the electric field, you see how these all have arrows pointing out? The direction of an electric field points in the direction that a proton would take. So if I was a little proton sitting right here, I'd travel that way. If I was a proton sitting here, I'd travel that way. Okay? Because I'd be repelled because this is positive, so it points out of positive and into negative. Alright. So, electric field lines. Out of positive, into negative. If you have positive and negative, it's going to point out of the positive and into the negative. Out of the positive and into the negative. So if I was a little proton sitting right here, I would travel out here, and then I'd get caught into that pull of the negative charge and go down. Whee! Okay? Now, if we have two of the same charges, then your lines push apart like this. Okay? So, a proton that was sitting right here would get pushed away from this one and pushed away from that one to travel like that. Okay? Now, for parallel plates. Parallel plates are basically like this is a conductor, and he's all filled with positive charges. This is the plate, and it's filled with lots of negative charges. So we end up with parallel lines. Now, if the closer the lines are together, the stronger the electric field, then the electric field between these two, anywhere between two parallel plates, is the same. Another thing to note, these lines, they never cross. So when drawing electric field lines, they should never cross. Now, we like numbers when we're dealing with things in physics. So we have an equation. The electric field strength in units of newtons per coulomb equals the force felt by the charge in newtons divided by the charge itself in coulombs. Alright, electric field equation. We have this equation, which tells us that the greater the charge in the same electric field, okay, as we increase this and E stays the same, F would decrease. Or sorry, F would increase. Okay, so the greater the charge, the greater the force felt. The greater the electric field, the greater the force felt. But if we were to link these two equations together, and we're going to substitute Coulomb's law in for the force, then E equals K Q1 Q2 over R squared divided by Q. Now, one of our Q's cancel, and you end up with it equals K Q2 over R squared equals E. So the electric field equals the constant times the charge of the object, of the charge making that field, divided by its distance squared. That equation is not in your reference table, but it is useful, and you can get there quite easily. Alright, so what is the electric field strength? If an electron feels a force of 1 Newton, is a distance of 1 centimeter, 0.01 meters, from the source, what is the magnitude of the charge? Alright, well, we're dealing with distance, so we know we're not going to be using this nice, pretty, simple, easy one, but we can use this one. E equals kq over r squared. Okay. We're gonna end up with a little bit of an issue. I asked 2 questions. I asked what is the electric field strength and what is the charge. So E equals 9 times 10 to the 9th. So that's K times Q divided by 0.01. Okay, now if we look at the other equation, E equals F over Q. So E equals 1 over Q. We have 2 equations, both equal to E, right? So we can set them equal to each other. So 1 over Q equals 9 times 10 to the 9th times Q over 0.01. Bring Q up to the top, and you get 1 equals 9 times 10 to the 9th times Q squared divided by 0.01. Okay, we solve for Q, and we get Q equals 1.054 times 10 to the negative 6th. Now if E equals 1 over Q from here, then E equals 9.5, I'm going to round. It's 948,683. I'm going to round to 950,000 newtons per coulomb, and charges in coulombs. Okay? So, that's an example of using both of the equations. Alright, that's all for the lesson. Good luck on your homework.